This is a three-part tutorial using FLAC2D to calculate the total and effective stresses and water flow for a two-dimensional analysis of a homogeneous embankment dam. This initial analysis is a frequent problem encountered in dam engineering and one that can be solved in a relatively straightforward manner in FLAC2D. Please note that the model developed was selected to have less than 1,000 numerical zones and therefore can be completed using the free demonstration mode version of FLAC2D available. Subsequent applications of this analysis are varied. With this initial analysis conducted, more complex analyses of the embankment with FLAC2D are possible. A few examples are provided here: gravity-driven instability, rapid drawdown, and earthquake-induced deformations. Let us revisit the problem. The homogeneous embankment dam that will be analyzed has a height of 65 feet and a crest width of 50 feet. The slopes are 2.5 to 1 on both the upstream and downstream side. The reservoir surface is set to be 60 feet above the toe of the dam. A blanket drain is located beneath the downstream toe of the dam and extends 50 feet underneath the embankment. The phreatic surface is shown and can be determined using traditional flow nets. Also included are the flow and equipotential lines nearby point A, a point for which stresses and pore water pressures will be calculated. The flow into the drain, Q, is also shown. Typical properties for the embankment are provided here, and anisotropic permeability has been assumed. In part 1 of this tutorial, we will be calculating the stresses in the embankment prior to the reservoir being added. Please note that in this video, the individual steps are briefly discussed and outlined, after which the actual execution of the steps in FLAC2D are provided. With FLAC2D open, click New Project. Navigate to a preferred folder location and then type the name of the project file, such as Embankment Analysis, and then click Save. Now click Select Content, and then New, and Sketch Set. Enter a name of the sketch set such as Sketch 1 and click OK. When the Important Note warning is provided, click OK. Or if desired to not have this warning appear again, click Do Not Show Again, and then OK. The Sketch tool in FLAC2D provides a quick way to develop a structured or unstructured mesh. In this example, an unstructured mesh will be created. Before interacting with the Sketch application in FLAC2D, key input parameters that will be used within Sketch will be presented and discussed. To begin, the boundary of the mesh will be defined by 7 points connected by 7 line edge types. It is advantageous to label each edge type and the entire domain with group names for ease of later command assignments. The edge group names used are base 1, base 2, downstream, crest, upstream 1, and upstream 2. The entire domain is called embankment. There are many parameters available in Sketch to control the characteristics of the mesh generated. In this example, the mesh configuration will be controlled using the zone number object property for each of the 7 edge types. The values that will be used for each of the 7 edge types are provided in the table shown to the top right. Now it is time to use the Sketch tool to develop the numerical mesh. With the grid snap on, click the Polyline tool and then draw the approximate shape of the embankment with the 7 points identified previously. Complete the shape by clicking the initial point again and then click Escape. We now have a rough sketch of our boundary. Next, we will refine the rough sketch with the precise coordinates presented earlier. To accomplish this, click the point and then either enter the exact XY coordinates beside position in the object properties, or right-click on the point, click Edit Point Properties, and then enter the exact XY coordinate here. Repeat the steps for all relevant points. Click the Reset View button or simply type Ctrl-R to reset the view if needed. For each edge type, now assign the group name and the zone size. Click the 7 edge types and then specify object properties discussed previously. It is now time to create the mesh for the domain. For this analysis, an unstructured mesh composed of only quadrilateral zones will be used. For this to be achieved, go to Meshing Parameters and then select Create Unstructured Mesh Only and Use Only Quads in the Unstructured Mesh. As seen, additional mesh controls are provided within the Mesh Parameters dialog box. At this stage in the model development, the domain can be meshed. This can be achieved within the dialog box by clicking Mesh Now, or alternatively by clicking OK, and then Mesh All Blocks. Now that the domain has been meshed, click the mesh and then under Properties type Embankment beside Group to create an embankment group for later command assignment. At this stage in the development of the numerical mesh, additional parameters may be used to further refine the characteristics of the mesh. In this example, the current mesh will be used. We have now finished with using the mesh tool. To produce the numerical zones for the numerical analysis, click Create Zones. Now click File and Save Project. Click Yes, and then enter a name for the save file that contains the information associated with this numerical mesh. The name used in this example will be Mesh. Type Mesh and then click Save. With the numerical mesh created, FLAC2D commands will be used for the additional numerical analysis steps. The commands will be contained in one or more data files. To create a data file, click File, or the drop-down menu, and then select New, and then Data File. The first data file in this analysis will be 1_static analysis. Enter the name and then click New. A text editor will now be provided for typing and then executing the FLAC2D commands. Note that the command-driven approach utilized in FLAC2D is very powerful, but does differ from FLAC 8.1, for which the user can set and control the analysis with typed commands, but also with a graphical user interface. It is worth noting, however, that in FLAC 8.1, if more advanced modeling complexities are required, type FLAC and fish commands will be needed to be used, and in this way the approach with FLAC 8.1 is very similar to FLAC2D. Also note that the commands in FLAC2D and FLAC 8.1 differ, with the FLAC2D commands following the syntax in FLAC3D. In fact, the FLAC2D commands are relatively straightforward to extend to FLAC3D. Like in FLAC3D, FLAC2D provides a rich and interactive means of exploring and understanding FLAC commands. For example, once the beginning of a command in FLAC is typed, such as zone grid point fixed, the conceptual help menu can be added to help with completing the command. Conceptual help can be added by clicking F1 when a command is typed, or by right-clicking on the command and then selecting Conceptual Help. In addition to conceptual help, a detailed help and documentation guide can be opened in FLAC2D by clicking Help and Help and Documentation. If desired, this documentation can also be viewed in a web browser. Now it is time to place the FLAC2D commands in the data file 1_static analysis to calculate the total stresses in the embankment due to gravity. These commands will be presented next with customized syntax highlighting and figures to help connect FLAC2D commands to the analysis problem. The first command, model new, will ensure that this analysis is beginning with a new model. With a new model, we now restore the numerical mesh created using the sketch tool with the command model restore mesh. This analysis will be configured for mechanical and fluid flow calculations, with the latter option specified using the model config fluid command. We now specify the constitutive model that relates stresses and strains. For this analysis, the isotropic elastic model will be used for the embankment zones. This option will be specified with the zone C model, elastic, range, group, embankment command. The range group embankment part of the command allows us to specify the isotropic elastic model to the embankment only. In this analysis, since all zones are embankment, this additional part of the command is unnecessary, but included here to highlight the use of the range group command. With the range group command, customization assignment can be produced based on the group names. For example, if a shell and group names were assigned as part of the meshing option in Sketch. We now specify the material properties for the embankment. The required properties are density, shear modulus, and bulk modulus, none of which were given directly in the problem statement, but for which can be computed simply as follows. Mass density, 3.73 slugs per cubic foot. Shear modulus, 3.73 times 10 to the 6 pounds per square foot. Bulk modulus, 6.23 times 10 to the 6 pounds per square foot. The properties will now be specified to the zones with the command zone properties, density, 3.73, shear, 3.73 e to the 6, bulk, 6.23 e to the 6, range, group, embankment. Next is assignment of the boundary conditions. For this analysis, boundary conditions will be assigned to fix the displacements of the nodes and grid points along the base in the x and y directions. In FLAC, displacements cannot be fixed, but velocities. However, if the initial velocity is set to 0, and the velocity remains fixed to the initial value, that is 0, the result is the same as fixing displacement to 0. Velocity will be fixed along the grid points at the base of the model. The range command can be used to specify the grid points for which the velocity will be fixed. Several range type commands are possible, but in this example, the zone face group names along the bottom boundary will be used, base 1 and base 2. The commands then become zone grid point fix, vel, 0, 0, range group base 1, and zone grid point fix vel, 0, 0, range group base 2. Note that since velocity is fixed in both directions, the vel command without 0, 0 could have been used. Many other such commands to fix velocity can be explored using the conceptual help or the help and documentation page. Now gravity of 32.18 feet per second squared for the model will be specified. The command is model gravity 32.18. With this set of analysis configured for fluid flow, FLAC initially sets the degree of saturation of the grid points as 1. As will be discussed in tutorial 3, the value of the degree of saturation will affect the density used in FLAC and the calculation of stresses. If this analysis is intended to mimic a dry embankment, that is, degree of saturation of 0, then the saturation needs to be reinitialized to 0. This is accomplished using the zone grid point initialize saturation 0.0 range group embankment command. We are now ready to conduct the analysis. The last step is to set a few key analysis settings. 1. Model fluid active off to turn off fluid flow calculations. 2. Model mechanical active on to turn on mechanical calculations. And 3. Model large strain off to turn off large strain calculations. We will now solve for static equilibrium using the model solve command. Note that static equilibrium is achieved iteratively using local damping. These iterations continue until the mechanical ratio is less than a set limit. Currently in this analysis, 1 times 10 to the minus 5. Once the solution is found, the final step in this analysis is to save the state. This is accomplished using the model save 1_static analysis command. The set of commands discussed previously will now be shown in the data file in FLAC2D. Once the set of commands has been typed, click the green arrow or simply click Ctrl E. You will see a cycling info dialog box open that presents the results during cycling. The model results at the end of cycling have been saved in 1_static analysis. To view the model result, FLAC2D has an advanced set of plotting tools similar to those in FLAC3D. We will utilize these plotting tools to provide contour plots at the end of cycling for the horizontal effective stress, vertical effective stress, and shear stress. The name of these plots will be 1_ESXX, 2_ESYY, and 3_SXY, respectively. Note when following the steps about to be shown in this video, the volumetric averaging will be used as the contour method, and maximum, minimum, and interval values will be specified. The reversed setting will be used in some cases. Each new plot is created by clicking the drop-down arrow, then New, followed by Plot. The last plot that will be added is the displacement vector. In this plot, displacement vectors will be added to a transparent mesh. In addition to the size of the vectors being proportional to magnitude, the by magnitude option will be selected so that the deformations can be better understood with colored arrows. To save the creation of these plots, go to File and then Save Project. Multiple windows within the workspace can be created to view together. For example, multiple plots and data files. Here, the 4 plots are shown. Additional workspace can be produced by unclicking Project, Command, and Tools. These items can be added again at a later time. This completes the first step of our analysis, establishing the stresses in the dry embankment. In the second step, completed in the next tutorial, a steady-state seepage analysis will be conducted to calculate the pore water pressures in the embankment due to the reservoir. In the third step, completed in the last tutorial, soil densities will be updated and the effective stresses in our model recalculated.